right? So that's why maybe not everyone is here. Okay, let me first review a little bit what we need from what we saw. So we saw that Lie algebra G is semi-simple if and only if the killing form is not degenerate. But sometimes one can take this as a definition, although I proved it. What else did we prove? What semi-simple Lie algebras? Ah, yes. If G is semi-simple, I can decompose it. This implies that G is a direct sum of simple ideals. Unique up to order. So this was the second statement. Particularly it meant that every simple ideal of G is one of those. What else do we prove? Ah, yeah, the next statement was G comma G is equal to G. Right, which follows from this here, because for a simple Lie algebra, this would be an ideal. So it's either 0 or everything. If it's 0, it's abelian. And that's not allowed for a simple one, so it must be everything. So this just follows from that. And I think there was one more we proved. Yeah, out G mod in G is discrete. Which wants that every derivation is inner. So these are the form at x, where x lies in G. All derivations look like this, which is another important property. So that's what we proved by semi-simple ones. And I think there was one more thing we proved. So we talked about compact Lie algebras. Remember, G is compact. If there exists a G compact with Lie algebra G. Par? Yes?
I'm not sure if the sort of the problem that G is rooted or not. It's not.
It's not in general, yes.
So this quotient is not named for.
That's correct. That's correct. It was a mistake in the notes, yes. If it is, then it's normal. As a group, it's normal. If it's closed, it's a manifold. It could be manifold without being closed, but it's only a Lie group with Lie algebra, the quotients, if it's a Lie group. And that's not always the case. Do you know a counterexample? Probably think in solvable or nilpotent Lie groups, I think one can find counterexamples. But I don't know offhand, but it's not true in general. So that's a mistake making the notes. But here, the claim is discrete, and part of the statement is that indeed this here is a Lie group. If you want to, this is the identity component of this Lie group. So when you divide, so it's certainly a normal subgroup. It's closed because it's an identity component. So quotient is a Lie group, but it's a zero-dimensional manifold, and it's just discrete. Okay. But in general, yes, there's a problem. So Lie algebra is compact if there exists a compact Lie group with Lie algebra G. And then we proved that G compact implies that there exists an inner product on G such that ad x is Q. Like in the killing form. But now assume it's an inner product, so it's positive definite. And ad x is Q. That's a very strong property. You use this all the time. This kind of Q symmetry is a very powerful thing. And the corresponding statement of the Lie group was that if G is compact, there exists a metric such that left translations and right translation are symmetries. But the important one for us is this one right here, that I can use this inner product. There was one more we proved. If G is compact, the center G finite or discrete, or finite, this implies that pair 1 of G is finite. And hence, the universal cover is compact. So for a compact Lie with finite center, the universal cover is a compact Lie group again. That's another way of seeing that statement. So that's also a very useful fact. Particularly from that, it then follows, since this is a finite cover, and this has finite center, the universal cover also has finite center. So there are only finitely many Lie groups with that Lie algebra, and they're all compact. Okay, so I think these are the things we proved. Let's derive some consequences from this, some simple consequences. First is that Killing form is negative definite if and only if G is compact, the center of G trivial. And by the way, so we're going to see in the proof that it never happens that the Killing form is positive definite. It's never an inner product in that sense that it's not positive definite. But minus of it would be if it's negative definite, right? So that's one useful statement. And B is that if the Lie algebra is compact, this implies that G is isomorphic to the center of G plus the commutator algebra. And the commutator algebra is semi-simple. So compact Lie algebra is the direct sum of its center plus something semi-simple. So it's essentially semi-simple. Compact and semi-simple is essentially the same up to this kind of trivial kind of factor where you have some possible center. So the proof is kind of typical in which we use this result right here, that like there's some inner product where Ajax is skew-symmetric. Right? It's not B yet. So let's see, and let's do this direction first, maybe. Certainly center is trivial, that's clear, right? Because otherwise it lies in the kernel of the Killing form, and it's negative definite, so there's no center. Here, this means we have to construct a compact Lie group with Lie algebra G. Right? So to somehow find one from the assumption that B is negative definite. So that means, of course, so minus B is positive definite. It's an inner product. Ajax is Q. And I claim this implies that so of course I also know it's semi-simple, right? Because it's negative definite. Semi-simple was non-degenerate. Semi-simple, I have an inner product. Ajax is Q. Semi-simple implies that out G, what in G, is discrete. Yes, out G are isometries in the Killing form. That's true for any Lie algebra. The automorphisms are summed in the Killing form. We used that before. So that means that since B is negative definite or B is positive definite, these isometries lie in the isometry group, so in the orthogon group of the Lie algebra with the inner product minus B. So the orthogon group of a positive definite inner product, and we know this is compact. And out G inside endomorphisms of G was closed because it's defined by an equation. So intersect with a compact group, that means this is also closed. Particularly compact, so out G is compact. And in G, because I know that out G is out G mod in G is discrete, so that means that in G is the identity component of out G. Right. In G was by definition connected. Out G may not be connected. It is compact. That means the identity component is compact. But what's the Lie algebra of this? Lie algebra, these were in G was things of the form at X, where X lies in G, inner automorphisms, inner derivations of the Lie algebra. And now notice that if this is isomorphic to G, because if I send X to at X, the kernel is trivial, because it's its center. And only an at X is zero, lies in the center, but the center is trivial. So now I have my Lie group, right? So in G has Lie algebra isomorphic to G. And is compact. So not only is there a compact Lie group, there's actually a very natural one, the inner automorphisms of the Lie algebra is a compact Lie group. Because then this one here says that where is it? That every Lie group with Lie algebra G must be compact now. Other direction, I think that's probably the one that uses Q symmetry. We want to say G, other direction is G compact plus trivial center. Implies that B is negative. But that's a useful trick to see. First, so we can choose an inner product on G such that at X is Q. That's what we hoop right here. Not the killing form, because that may not be an inner product. So I want something that's positive definite, so there exists one where at X is Q. And now I claim that this implies that if A is an ideal in G, then A perp is as well, and G is A plus A perp. Maybe we did this last time for semi-simple Lie algebras. We proved that I can split it up into simple ideals by showing the orthogonal complement on D as an ideal. And this same proof, since we only used at X cube. So if you go back to that proof we did last week, that this year we used at X cube all over the place again and again. And now we have an inner product where that's the case, so that's good enough. You don't have to use a killing form. And that means I can now split off the center. Let's see, what are we trying to prove? Pardon? No, we don't need that. We don't need that yet. What are we trying to prove? We're trying to prove B is negative. Yes. So let me erase that. That's not what we need right now. Right. So what was B? Let's compute B. Right. B of x comma x was trace of ADX ADX. But it is true that we have this inner product here where ADX is Q, so I can say this is minus trace of ADX ADX transpose with respect to the inner product. Plus ADX is Q, right? So now I put those two together. Well, we just said that, right? So let's just think about in general. What's the trace of, what can I say about the trace of A transpose when A is a matrix? It doesn't even have anything to do with being skew. What is that? Trace of A transpose for any matrix A. So in terms of the coefficients of A. It's actually a very nice thing to study. Actually, it's like an inner product. Because I claim that this is summation Aij squared, where A is Aij. So crank it out. It's very easy to compute. Because it means, for example, it's greater equal to 0. And equal to 0 if and only if the matrix is 0. So in complete generality, this is an inner product. On the set of all matrices. Right? Very useful inner product one can use for all matrices. So that's what this looks like here right now. It's up to a sign here. It's trace of an endomorphism times its transpose. Right? So by this observation here, this implies that E of x comma x is negative and equal to 0 if and only if ADX is 0. But ADX 0 means x lies in the center. We assume the center is trivial. Which means if and only if x is 0. And that proves it. Right? So now we have, it's small equal to 0. That's what we said here. It's greater equal to 0, negative is small equal to 0. It's 0 if and only if the endomorphism vanishes. So I get a 0 here if and only if this is 0, which is x in the center, which means x is trivial. So now this implies that B x comma x is negative. Negative definite in the usual sense. Okay, so that's a really useful fact. And then I can use B as an inner product. That's why it's so useful. Let's do one more application of that. Kind of classification of compact Lie groups, if you want to. So if something is compact, implies universal cover is Rn cross G1 cross Gk, where the Gi are compact and simply connected. So this, of course, is something that comes from the center. Right? So that's something we know already. But the rest are compact, simple, and simply connected. That's a really strong statement. Particularly reduce, so compactness here is maybe even the most surprising one if you want to Right? The universal cover consists of compact groups. And so it reduces classification of compact Lie groups to those which are compact, simple, and simply connected. And that's something one can do. Proof is very easy. Just combine everything on the blackboard now. So first, G compact implies that that G is compact, right? Which implies that G is the center of G plus something semi-simple. So that means I can split up certainly already G tilde as Rn cross, say, G prime, where the Lie algebra of G prime is G comma G, and in particular semi-simple. That's what, where is it? Somewhere we proved that. Here we go. Here. The center plus something else, the commutator, and the commutator are semi-simple. That means that D prime, since it's semi-simple, I can now split it up into simple ideals. So now, what does that mean? So now I'll let, let's see, which way around should I do that? A are going to be the Lie algebras with Lie, are going to be the GIs, the Lie algebra of the GIs. Yes, so I have right. G prime was Rn times G prime. And I can now let Gi contained in G tilde be the connected Lie groups with the Lie algebra Ai. Now I can use Weil's theorem. Let's see. So Gi is semi-simple. It's a commutator. Did I erase it? I think I erased Weil's. Here it is. Say that again? What did you say?
G prime is isomorphic to the draw of the GIs.
That's what we're trying to prove, right?
Because the products of the GIs are, I can choose the GIs to connect and the reaction of this product is that.
Well, of course, Gi is a subgroup with Lie algebra Ai, so it may not be simply connected yet. But I want to claim I take the universal cover, make it simply connected, then it should still be compact. And for the universal cover to be compact, I'm going to use Weil's theorem. So certainly the center of Ai is trivial. Why is Gi compact? Yes. G prime was a direct sum of ideals. All these are simple. Let's see. Killing form is negative definite. That means the killing from the air is negative definite also. And that meant that proved that somewhere, right? Or where do we prove something? That the Lie algebra is compact with center 0. So we have a compact Lie algebra with center 0, which means the corresponding Lie group is compact with finite centers, since the Lie algebra has trivial center. So that means that pi 1 of gi is finite, or gi tilde compact. And now I can take a foreign kind of homomorphism. Into I will now show that G tilde is a product. I won't define a covering, but just taking the product. I want to show that pi is a covering, which then means that pi is an isomorphism because this group is simply connected. So this was a product of Lie groups, right? So that certainly means that this is a homomorphism when I multiply. These are also ideals, right? This was a direct product of Lie groups. They're ideals. So I can interchange any of the two here, right? So that's certainly homomorphism. So that's clear. All I need to show that d pi is an isomorphism. Right, this would then imply that's a covering. But on the Lie algebra level, of course, G tilde, the Lie algebra of G tilde, was simply Rn, direct sum with the AIs, right? And the AIs are the Lie algebra of the GIs. So that means it must be an isomorphism, and that implies it's a covering. And then this is simply connected, covering is trivial, so that means G tilde is a product. So this Bayes theorem here is a strong, strong property. Helps you reduce the classification of compact Lie algebras like this. Okay, let's now get to the central part about compact Lie groups, which is what is called the maximal torus theorem. So let's first think about the Lie algebra. So I have a compact Lie group. I look at the Lie algebra G, and then I can look at subalgebras inside G which are abelian. So let's look at all A contained in E which are abelian. Subalgebras, not ideals. There could be lots of them. I want to understand how many there are and what they look like, and they're actually simple to understand. So I look at, say, let's call it T inside G, a maximal abelian. Subalgebra. Certainly every abelian might be in a bigger abelian, in a bigger one. Look one that's maximal under inclusion, right? In that sense. It's not unique, right? If I start with a different abelian, Lie algebra, if I then increase as much as possible, I get something different. Right? So at the moment it's not unique, but I want to understand these kind of maximal abelian subalgebras. And the theorem is the following. So let T inside G maximal abelian and G compact, or in other words, Lie algebra compact. Then part A is that first, we're going to make into part B. Let me write down part B first. How unique are they? They're unique up to conjugacy, right, in the sense that if T1 and T2 are maximal abelian, then there exists an element in the group such that at G takes T1 to T2. That's certainly the most thing, the only thing you can expect, right? If I take an abelian Lie algebra and I apply at G to that, I get another abelian Lie algebra. Right, so if at G T at G T, well, at G are homomorphisms of the Lie algebra, so it's the same thing as at G T comma T. So this is 0 also. So you can move them around with the adjoints, there are lots of them. And they're unique up to that kind of obvious change. That's what this is. And the part A says the following thing, that if X is an element in the Lie algebra, then there exists a G in the Lie group such that at G of X is an element of T, of my maximal abelian subalgebra. One consequence, a corollary, is that the dimension of T is well defined. That's what follows from part B. It's unique up to conjugacy. So they all have the same dimension, and that's called the rank of G, of the Lie group or the Lie algebra. Same thing. So they all have a certain rank. And the smaller the rank is, the easier they are to understand. So let's think about this first part, maybe to see why it is interesting before I prove it. So part A helps me understand the orbits of at in the Lie algebra. Right, so in the sense, let's take an element in the Lie algebra and look at G applied to the vector X. That's an orbit of the action on the Lie algebra. It acts in the Lie algebra via the adjoint. I take an orbit on it, under it, and it's inside G, right? For example, G is compact. This is a compact submanifold inside G, right? Now I want to understand the decomposition of this vector space into this decomposition of orbits. And that's often very useful. These orbits also have wonderful properties. They occur all over the place. For example, they're symplectic manifolds. Right? They are Kähler manifolds. All kinds of wonderful properties. So I want to understand what these orbits look like and describe them somehow. And what this here says that every orbit goes through the maximal abelian subalgebra. So in other words, I can say, well, at Gx, it meets the maximal abelian subalgebra, so I can also describe it as at G of, say, element y, where y is some element in the maximal torus. Right, just write x as at G of something in the maximal torus. Right, so in the sense, well, I know that at G of x is an element in T for some G, that's what this is, call it Y. So then the orbit at G of x is equal to at g of at little g of x, which is y, because at g times at g is the same thing, right? It's a homomorphism. So everything goes to this kind of a linear subspace inside the Lie algebra, usually of very small dimension, and everything intersects it. Right? So understanding these orbits of things in the maximal Abelian subalgebra is all I have to do, and they're much easier to understand. We're going to try to see what they look like a little bit later. Okay, so that's one of the reasons why this is very useful. And in fact, this kind of construction helps you classify compact Lie groups. You're going to do it via the maximum Abelian subalgebras. By the way, so in this context, another interesting question is, so I have this linear subspace T, right? Every orbit, at G orbit meets it. Here's the point Y, right? You can even show it meets it orthogonally when it meets it, although this won't be important to us. But of course, it might come back, right? So the picture might look like this, that somehow the compact suborbit comes back and meets it several times. Right? So this intersection point is not necessarily unique. And the question, in how many points does it intersect it, is very important. It's going to give rise to something called the Weil group. So this geometry we're going to understand in even more detail. So the geometry, the adjoint orbits, we're going to understand in more detail, which is important. In fact, let's think of an example maybe. So let me go on a little bit. Let's say the Lie group, simplest example is SO3. Let's take the Lie group G. I want to understand the adjoint orbits. And here they're very easy to understand. So first, from where to where does at go? At goes from the Lie group SO3 into the isometries of the Lie algebra. Right, this is a compact Lie group, so it has an inner product that's invariant under adjoint. Right? So adjoint goes into the orthogon group, and it's a homomorphism. What's the center of this homomorphism? What's the kernel of the homomorphism? That's the center of SO3, but we saw that's trivial. So in fact, this is an isomorphism. So at is an isomorphism. So therefore, adjoint is just SO3 acting on R3. So adjoint orbits are the orbits of SO3 acting on R3. And what are they? What are the adjoint orbits SO3 and R3? Spheres, just spheres. So there are two spheres of radius r inside R3. And how can I view this in this kind of language that we discussed over there? What's the maximum abelian subalgebra inside SO3? So it's a three-dimensional Lie algebra. What are the subalgebras that are abelian? You probably have done this computation, or we did it. So I can view this, say, as three vectors, right? The matrices which are skew symmetric. Right? So then put it in the other coordinates also. Right, I get 3 vectors like this. And then this third one is, where can I put it? So that's a basis. The set of skew-symmetric matrices, 3 by 3 skew-symmetric matrices. And then a simple computation shows that x, y is equal to z, and then cyclic. So the x, z is equal to y up to sign, and x, y, z is x up to sign. So 2 of them always gives me the algebra, a second one, right? So there's nothing that commutes. At a maximum Boolean subalgebra, I cannot find 2 vectors that commute. What does that mean? Just one-dimensional. Right? So T is equal to R. And in fact, this theorem here says that it doesn't matter which one I take. Any real line in R3 is a maximum Boolean subalgebra. It's one-dimensional. Right? If I apply ATG, I get any other one, but ATG are rotations in R3, so every line gets taken to every other line. So T is any line in R3. So I can, for example, take this, say the z-axis. Right? This is my T, my maximum Boolean subalgebra. Orbits are spheres. And now notice that the sphere meets my maximum Boolean subalgebra always in 2 points. Right? Everywhere meets in 2 points. So that's this kind of question I just asked. Well, how many times does it meet it, or where it meets it? Right? You can see that it's usually in many points. It's not unique, right? Here, even the simplest example meets it in 2 points. In other examples, it's more complicated. We'll study that. So here's a really simple kind of picture of what adjoint always look like. Okay, let me give the proof of the proposition. It's very geometric. For those of you who've taken, say, a course on Lie algebras only, the analogous thing that one proves is that if you have a complex semi-simple Lie algebra, then you also have a Cartan subalgebra. Which I won't define it now, I'll talk about it later. And the existence of Cartan algebras and the uniqueness of the conjugacy, so the analogous theorems in that situation, that's expensive to prove. Right? You have to work. It's not easy. I'm not going to do it in this course. This one's easy. Because then I can complexify, so and then I get a corresponding thing for complex Lie algebras. So I'm actually doing the Cartan subalgebra geometrically. Okay, let's start with A. So what's the idea with A? So I have my maximum Boolean Lie algebra. I take some point in the vector space. I want to claim that I can rotate it with adjoint into the algebra T. So let's see how small I can make the angle, right? Make the angle equal to 0 if you want to, between this linear subspace and that vector by conjugate. Make the angle smaller and smaller. If you can make it 0, you're in it. That's the idea. So I want to minimize a function. I want to minimize the angle between the vector and the maximum Boolean subalgebra. That's the geometric idea. So I define a function from G to R, which takes G into the angle. And I do it in terms of inner product. At G X with T. So here somehow, how do I compute the inner angle? You have to choose something clever. And here's a clever choice. I'd like to put a vector in there as opposed to a vector space, right? If you want to, see if I want to compute the angle between a vector and a linear subspace, what would I do? I have to somehow take the projection, right, and compute the angle. But to take a projection, I would have to choose an orthonormal basis here and then project, right? That's kind of not so nice. I want to write an explicit function. That's not so nice. Because I want to compute its derivative, right? Then afterwards, I want to take a minimum of the function. G is compact as this, the minimum. Compute the derivative at minimum. and then show that it means that it's 0, and therefore it lies in T. So that's the idea. But technically, we do the following trick. Like, this is a trick we're going to use frequently. It's kind of very nice. So we have T inside G. That means we can look at xt inside the Lie group G. Right? This is a certain subalgebra. Let's call it a subgroup. Let's call it capital T. It's connected in abelian. Because T is abelian, right? So if I take X for something abelian, that's abelian. Remember, we proved that X is an exercise so X of this abelian subspace is an abelian subalgebra inside G. But it may not be compact. So what I do is I'm going to take the closure as a subspace. So here I meant, so T is the image, right? X T as a subgroup inside G, as an abelian subgroup inside G. I call that capital T. I take its closure as a set. That means I claim it's still an abelian group. Right, so it's a limit of things inside xt, so I can certainly still multiply. I take two things in the limit, write them as limits. I can multiply inside, I can multiply in the closure. If everything commutes and I take limits, then everything commutes to the limit also. So it's still an abelian subgroup, and it's connected. Because the closure of the connected set is always connected. So I get another abelian subgroup, and I claim that that T bar is equal to T, and hence T is compact, because T bar was closed. Well, if not, T bar is bigger than T, but these are both connected. So how can two connected subgroups be bigger than the other one? The Lie algebra would have to be bigger. Contains G non-trivially. How do you write that? Because if they're the same, otherwise a connected subgroup is the same. That corresponds to that Lie algebra. Right? And that contradicts, of course, here we have the Laplace were called T. Here it was T. But T was maximal. So G bar must be equal to T. So that means that T bar had to be equal to T. So just take the closure, I get something bigger abelian. That can be because T was maximal abelian, and therefore this is closed. Right, so this is closed, it's also compact. So T equals X of T is compact. So compact abelian group. Remember, you proved that these are isomorphic to a torus. Just a standard kind of torus. Right? That means the following. That means there exists a vector y in the Lie algebra such that if I look at the one-parameter group, this is dense inside this inside T. Right, so just think of it, say, it's like an irrational slope thing, right? If it was a two torus, I would take a line of irrational slopes. But what are one-parameter groups? In this kind of abelian group, the most cover is Rn. I just take a line Rn. Image in the torus is some kind of some line, an image of a line. If it has irrational slope, then it's dense in the torus. The claim is the same thing is true for a high-dimensional torus. Make all the coordinates irrational, or something like this. Right? Then it's completely dense in the whole torus, even if it's higher dimensional. C was just dense in the two torus. Okay, so that's the thing that we want to use. I have a one-parameter group that's dense in the two torus. And that's what I take the inner product with. Why do I do that? Why is that a good thing to do? I claim because this element y is a following property. So fix this y, right? Fixing this y where whose image is dense. So I claim that if Z is an element in G and Z commutes with y, this implies Z lies in T. Right, y was in T. That's kind of surprising. Equals 0, sorry. That's kind of surprising, right? Certainly everything T commutes, so if Z lies in T, of course the lead vector is 0, but I can't choose another vector that vanishes with everything. That you wouldn't expect in general. If I take a maximum B in subalgebra, I take something outside of it, and it commutes with it, with a vector inside there. It doesn't have to be the maximum B in subalgebra. So that's the important property. Why is this true? Well, what does it mean that Cy vanishes, the lead bracket vanishes? Or now use the fact that it's dense in the torus, or to show that it commutes with all of T. So that's the goal, I think. So the goal should be, let's try to show that this implies that the vector Z are fixed with everything in T is 0. And then, of course, by maximality, this would imply that Z must be in T, because T was a maximum B on 1. So why is that? Because now I want to use that XTY is dense in the torus in order to see that. I guess I probably want to use this property to slow it down. This means that X of I guess, okay, maybe I want to show that XTZ, okay, I think that's maybe it, commutes with XTY. That's what I'd like to show, because this one's dense in the torus, it commutes with the whole torus, begins with T. That's this formula. Yeah, okay, that's the formula, right? X per TZ xtx, xty is xtx plus y. And of course, which is now equal to other way around, xty, xtx. So they commute. Right? This thing, they just commute. Okay. So by densence, this means that this xtx, xtz, that commutes with t. But this implies then I can now take the derivative, right? If I take the derivative, commuting means the Lie algebra, so this implies that the vector z commutes with everything in the maximal torus. And now I'm done. So now I can use maximality, then z lies in t. Okay. So that's the important property. How can I show that something lies in my maximal Abelian subalgebra? Just by showing that it commutes with a special vector, which is dense. That's all I need to show something lies in the Abelian subalgebra. It doesn't have to be commuted everything, which is what you would think. There's a special vector where if it commutes with that, it lies in it. So that's why I want to do this here. Like take an inner product with y. If I can show the angle is 0 with that, might be done. Okay, so now take a maximum to let G naught be, it doesn't matter, say min, max, actually doesn't matter, just the critical point. And I want to show that at G naught, x in a product with y is equal to 0. That's my goal. By computing the critical point. Well, this would imply now, if I can do that, right, y is my special vector, where if it commutes to that, it lies in the maximal Abelian subalgebra. This one would imply that at G naught of this vector x lies in, is an element in T. That's what I want to show. I want to show there's something which conjugates into T. This kind of vector is useful for all kinds of proofs. The fact that you have this kind of vector that's dense in torus, that's a very useful trick. So let's compute the derivative. Let me do it here. We show how we finish A, and then I'm going to come back to B. So let's create some room. So how do you compute such derivatives at the point G naught? But you have to go in the direction of a curve. So I want to compute, we'd say df at the point G naught applied to some vector. So I have to have a curve in the direction of this vector. Right? How can I create curves starting at G naught? Right? I could take one parameter groups. Right? That's my usual trick of how I create curves. So what's the one parameter group which has say a given vector and goes to the curve P naught? I claim I can do the following. I take the left invariant vector field at G naught, so C G naught is left invariant with Z inside the Lie algebra G. So if you wanted, that's the value at the entity. I then move it around by left translation into G naught. And every vector I can write in this form. Right? So every vector I can write in this form. So I want to take a curve tangent to G naught, to this vector field. But this is a left invariant vector field. I just take a flow curve. Right? What was the flow of Z? It was right translations by x, t, z. Turns out that's not quite such a good idea. I claim left translations are better. It's not a flow, but who cares? So I claim let's look at the following curve. In a minute we're going to see why it's a better idea. X per, so TZ multiplied by G naught. Let's see, is that okay? Let's see, is that what I want to do actually? Let me think. Actually no. I want to combine the adds. Okay. Right translation is actually better, so we can just take the flow. So that's then the gamma at 0. So when t is 0, I'm at the point G naught, right? And gamma prime at 0 is by definition the vector z. Since this was a flow, right? This was a flow of the vector field, so I just get the vector z at the point gamma 0, of course, which is z at the point G naught. So that's the curve I want to take in order to compute the derivative, right? So df at the point G naught applied to z at the point G naught would be d dt at t equal to 0. So let's plug that in. At G naught. Oh, well, yeah. To plug it in here, right? I take f of gamma of t, d dt of f of gamma of t. What is that? So it's f of this curve right here. xpz. So let's plug that in. It's actually a good example of how to take these kind of derivatives using all these kind of properties of exponential mapping now. So at G, but G is this here, so at G naught xpz. So that's what I plug into here, and then I apply it to x and take inner product with y. Okay. Okay. Because now I use the fact that the Addison homomorphism. Got the derivative. So I have to differentiate back to t. Now notice that y is fixed, x is fixed, at G naught is fixed, so everything's fixed except for this one right here. All right, so I have to take its derivative. And remember, d of at is little at. So it's like Lie bracket. So this is at G naught times so think of this here, I guess, right? Think of this. This is a vector inside the Lie algebra. And now differentiate with respect to t. So I get the Lie bracket between z and x, right? Because d at was little at, right? So I get little at z with applied to x, that's my Lie bracket. At t equal to 0. Right? And now an inner product with y. And so so now I compute the derivative, right? That's what my derivative looks like. But of course I want to use that it's equal to 0 because I'm at a critical point. So what I know about this is 0 for all z, right? Must be 0 for all z. So for all z in the Lie algebra. What do I want to show? I want to show this, right? Which meant here I want to show that this bracket vanishes. I want to look at G naught xy somehow. Well, this is an automorphism. I'm putting it inside probably. Let's try that. What could I do now? Let's see again what we want. We want the Lie bracket at G naught and x. So between at G naught x and y. Between at G naught x and y, right? That's the canonical bracket we want. So what do? Use Q-symmetry. Our most powerful tool is Q-symmetry. So minus y x. Sorry, did I do something wrong? What do I switch? I want at G naught x and y. So I switch these two, right? Okay. Inner product z with at G naught z. This must be 0 for all z. Well, if that's true for all z, at G naught z is then also everything, right? So 0 with everything, so it must vanish. But that's what we wanted, I think, right? So now that's what we proved. So it's very geometric, right? Minimize the angle, show it 0, then you lie in the Lie algebra. Much better than the existence of a Cartan subalgebra if you've seen that proof. It's very geometric. Then let's prove uniqueness. That's also expensive if you think about Cartan subalgebras. Let me write down again what I meant. That's actually now a simple trick. So what was it? If T1 and T2 are two maximal Boolean subalgebras, then they're conjugate. And there exists G and G such that at G, T0, T1 is T2. So unique in the best possible sense that one could expect. So this was B. Actually reduce it to A. I can play them off against each other, right? Each one's maximal abelian, so each one has a property that any vector can be conjugated into it. So let's see. I think I want to use this trick again. I can choose something in, let's see in a minute whether I need T1 or T2. Let's say T1, I may need in T2. Choose y in T1 such that x per Ty stands in the image of the maximum Boolean subalgebra. We saw we can do that. Therefore, if it commutes with it, it lies in it. Right? That was our trick. I'm going to show an inclusion. So the idea is show that this is contained in here, then do it the other way around, right? Let's see what I would need, so what I want. That's the idea. So I want to show this. Because I have to find the G, right? Okay, because every vector I can conjugate into T2. So I think I want to use T2 here. So take this as my vector X, or whatever we called it. I want to show I can, let's see. So if I take such a vector, then there exists I want to conjugate T1, T2, so I probably want to start with a vector X and T1. This implies there exists a G such that at G, X lies in T2, using the fact that T2 is maximal beta. Let's see. There was a little trick. So I want to use this denseness again. Showing that if something commutes with a vector, it lies in there. I think I want to use a vector, this dense vector, conjugate the dense vector into T2. So then I think I want to choose it in T1. Yeah, so let's take a vector in T1 with this dense. Now use the fact that T2 is maximal abelian. This implies there exists a G such that at G of this dense vector is an element in T2. So it means in particular that this vector has V bracket with 0 with everything in T2. Now use that at is a homomorphism, so put it on the other side. This means that Y at G inverse T2 must also be equal to 0. By pulling in at. Now I have something that commutes with my special vector Y, whose image was dense, so that must lie, therefore it lies at G inverse T2 is a subspace of T1. How can I finish now? I'm almost done, but not quite. One's contained in this one. I want to show they're equal. Yes. How do I know they have the same dimension? Maybe this is a subspace that has smaller dimension. Right, no, I've started out with two that are maximal abelian. I want to conjugate one to the other. Of course, they would have to have the same dimension for that to be true. But a priori, I don't know what dimension the maximal abelian ones have. Right. But what does this imply here? It implies the dimension of T2 is more than the dimension of T1, certainly, because Archie is an isomorphism. Right? Now what? Reverse the role. Right? So take a that dense vector in T2, conjugate it to T1, using that's a maximum being algebra, I get the other way around, at least inequality. I get a different element here, so I don't want to use the same element because I'm switching elements now. That's not a good idea. Right? But certainly I can use this just the same trick to say that this is bigger equal to dimension of T1. So therefore they're equal. That means the subplate must agree since they have the same dimension. Right. So I conjugate one to the other. So I use these special dense vectors both in T1 and T2 and play them off against each other that they have a special property. That's B. Okay. So maybe just mention something we're going to do next. I want to do examples next, but what's also important is that I take the image of this torus, right? So T inside G was maximum abelian. We then took a look at X of T inside the Lie group G. This was compact. Right? We showed that. So this is a torus. Connected torus and abelian. So that's called a maximum torus. And that torus is also important, the maximum torus, which is the exponential image of this maximum abelian subalgebra. Now maybe a question you can think about for next time. Could I do this the other way around? Could I say that is T the maximal abelian subgroup? Right, it's abelian. The Lie algebra is maximal. Right? I could also look at all subgroups, the abelian ones. Right? It has an inclusion. Right? I can always choose a maximal one. I could look at different maximal ones. Are they the same? And so on. So I could ask the same kind of question on the level of the Lie group. And the question is that true or not? If not, give me a counterexample. So I want to look at this maximal compact subgroup. And then in the classical Lie groups, I'm going to show what it looks like. Then we want to study the Weil group. So next week is examples in Weil group. Okay.